I'm back. I'm talking about the VSPER theory today. So if you guys remember, that's drawing the Lewis structure and identifying bond angles, molecular geometry, electron geometry, etc. So I found a very quick chart for you guys that helped me out a lot when it came to Gen Chem 1. And if you notice, they have the number of electron pairs, the bonding groups, so how many lines there are that you draw in between the central atom and the attaching atom, and the number of lone pairs, and what that helps you determine is the electron geometry, molecular geometry, and the rough bond angles. So just a quick throwback, these are the rules to help you guys figure out how many electrons you are drawing in order to figure out if you have any lone pairs or not. If you need to read them, pause this video now. Alright, so the worksheet that I was given to do for this asked us to identify the electron/molecular geometry along with the bond angles for the following. Now we have BH3, NH3, xenon tetrafluoride, and sulfur tetrafluoride. So the first things first, drawing the Lewis structure. So just keep in mind, guys, there are some elements in the periodic table that do not mind having a shrunk octet, so they don't mind having 6 electrons. So a classic example of that is BH3, boron. Boron's totally fine with 6 electrons, not 8. So first we're going to draw the electron groups, aka how many lines there are. And if you go back and look at the steps that I showed you, you can see that nitrogen, xenon, and sulfur, all of them have a lone pair or lone pairs. And all of that is determined by that math. So now we have to fill in the remaining electron/lone pairs and or elements. So for BH3, we needed to fill in all the hydrogens. For nitrogen, for NH3, we needed to fill in all the H's, so on and so forth. Alright, so now we need to identify the electron geometry. So again, boron is totally fine with a shrunk octet. It's BH3. It's only on a plane. Nothing's popping up. Trigonal planar. So NH3, you have 4 electron groups, but you have 3 bonding groups, so 3 lines, 1 lone pair. Either way, you still got 4, so it's tetrahedral. Now, xenon tetrafluoride is octahedral because you have the 2 lone pairs and you have 4 arms, so in total you have 6 electron groups, which will make it octahedral. And then for sulfur tetrafluoride, you have 5 bonding groups, but one of them is a lone pair, making it trigonal bipyramidal. So now we have to identify the molecular geometry. So one thing that I want to point out to you guys is remember how many lone pairs there are on each and every one of these in order to help you identify the molecular geometry. So just a quick check going back to this. As you guys can see, the first column is electron groups, so how many times or how many lines and or lone pairs are attached to the central atom. And the bonding groups is how many lines, and then how many lone pairs you have. Now, if you guys notice, some of these have electron and molecular geometry as the exact same, but that's not always the case. So a classic example would be the tetrahedral shape. So if you have 4 electrons and 4 bonding groups and no lone pairs, your electron geometry and molecular geometry will be the exact same. However, if you have 4 electron groups, 3 bonding groups, and 1 lone pair, your molecular and electron geometry will be different. And it's the same with octahedral. Octahedral is a little bit tricky. So if you have 660, so 0 lone pairs, your electron and molecular will be the same. If you have 651, your electron geometry and molecular geometry will be different. And here's just one hint, guys. Please notice this. When we get to 642, so 4 bonding groups, 2 lone pairs, the molecular geometry becomes square planar. So it's completely different. Alright, so next thing is to identify the bond angles of each of the following. So keep in mind, guys, the lone pairs will cause all of the bonding lines to shift and shift away from them. So essentially it's kind of like pushing the lines away from themselves, away from the lone pair, which causes the angles to equal a rough estimate, so roughly 109, roughly 107, etc. And as you can see Some of them are also exact. So BH3 has an exact bond angle of 105, I think that says. But if you look at NH3 where it has a lone pair, it causes the angle to change and be a rough 109.5. So that is it for the VSPER theory. I hope you guys enjoyed it. You are fully welcome to take the chart and the rules, and I hope this helped you guys out a lot.